grading done in my concrete and steel design classes over the past couple days. So I just wanted to sort of recap that with everybody and make sure that everybody's good with what's going on. So first off, let's talk about concrete, since we're in concrete design. We have homework number 8 due today. Homework number 8 due today. Homework number 8 due today. If you have not turned that in, please do so. Okay? So up there, I'll collect those at the end. As for today, I have returned exam 2, and I've also returned homework number 7. Okay? So in concrete design, we're caught up. Every outstanding assignment that needed to be graded has been graded. The only thing remaining is homework 8. I obviously haven't graded homework 8 since you literally just gave it to me. And then homework 9. Now homework 9 was activated today, turned on today, and it is due Friday, May the 3rd, our last day of the semester. So here's how this is going to work. Okay, and I want everybody to be clear on the logistics. We are going to press on in this class until we are done with beam columns. When we are done with beam columns, we will not meet again until Friday, May the 3rd. So if for some reason we finish beam columns on Friday, we wouldn't need to meet Monday or Wednesday of next week. I'm just going to go ahead and tell you that's not going to happen. Okay? But there's a very strong possibility we don't need to meet next Wednesday in here. Okay? Very strong possibility. I don't know. It just depends on how fast we get through things. That doesn't mean I'm going to rush because this stuff's on final. So you need to. I'd rather take my time. If we have to meet every day next week, I'd rather us meet every day next week because I don't want to rush through this stuff. Fortunately, though, it's really not very, very difficult. Okay. The last thing I want to talk about is this. So I mentioned course evals last time. Course evals, again, are something I take into consideration very, very highly. I pulled the count, and what I found is on course eval, 10 of you have done the course eval, but only 6 of you took the little picture and uploaded it to Blackboard. So 4 of you did the survey and haven't gotten your 10 bonus homework points as a result. So again, you could have raked me over the coals, but still upload the picture and you'd get free homework points. So that's all I would say there. So free homework points if you do the survey. But here's another thing. If everybody does the survey, if I have 100% response, I'll just give everybody their 10 bonus points. So, sound good? All right, so if you haven't uploaded the screen capture that says that you've done it, do so, and that's free homework points. If you haven't done the survey, do it and upload the picture, free homework points. But again, really, if you have like any significant suggestions, tell me about them because I really do take them into consideration. Okay. With that, I'm going to shut up and get back into concrete design. That's enough logistics for today. Okay. So last time what we did is we were looking at this particular example. I had a remote. I don't know where I put it. Oh, there it is. We looked at this example, and I don't think that the core component of the example was all that difficult. 0.85 FC prime times the area of the concrete, Fy times the area of the steel, and throw 2 little adjustment factors on there. One's our phi value, and the one's the alpha for accidental eccentricity. And that's it, What was a little nitpicky about that problem was the details, the little ACI checks that we have to do, but in the end, I don't even think that was terribly difficult. The only thing is I think it was, how shall I put it, just time consuming. So that was for a square or a tied column. Now let's look at spirally reinforced columns, and we defined these limits pretty rigorously last time. I just kind of want to review them to make sure that everybody remembers what we were talking about. Excuse me. So remember, a spirally reinforced column just behaves differently. It behaves differently because what's going on is those spirals are acting as sort of like a pressure vessel that's containing the core of that column. So once you load the column, you'll have that exterior concrete that sort of falls off, but the inside column, that spiral reinforcement holds everything together and combines it together so you can eke out a little bit more of an improved behavior out of the column. Now, in order to do that, you got to provide a lot of spiral reinforcement because you're trying to ensure that the spiral reinforcement can hold up 0.85 FC prime times the area of that core. Now, that reinforcement basically needs to meet the required ratio, assuming that this acts as a pressure vessel. So we solve for that theoretically, and we get a value that's 0.425 times the limit of that, or times those two expressions. What ACI says is, what the heck, let's just round it up a little bit to 0.45 times those quantities. Again, really straightforward stuff. Now, that box, keep in mind, that's the limit. That's the minimum amount of spiral reinforcement that we have to provide. This is how much we actually are providing. So, remember, a reinforcement ratio is just the volume of the spiral divided by the volume of the concrete. So, we're used to doing area of steel divided by the area of the concrete, but it's a little 3D here because we're talking about the steel going this way. It's wrapping around the column and it's going up, kind of like a big spring. So we take the volume of the steel as just the area of the bar times a single revolution, and then the volume of that concrete as pi d squared over 4 times the height as that rebar goes up 1 pitch. And just divide the two and do a little bit of algebra to simplify it, and that's the amount of steel we're actually providing. So that's how much we're providing. That needs to be greater than or equal to our ACI limit, and then you're good. Sound good? All right. Let's go through a pretty straightforward basic example on the analysis of a circular column. So I have a column that's 4 KSI concrete, 60 KSI steel. We have, now I believe it's 7 bars that are spaced equally around the column. That's another thing about circular columns, is that you can use like 7 bars and it's not that big of a deal. Like on a square column, it'd be kind of weird to use 7 bars. You probably want to keep it symmetric and keep it even, but that's no big deal for a circular column. So we have 1.5 inch cover. It's a 15-inch diameter column. We have a number 3 spiral that's going up the column that's pitched at 2 inches. Now we're going to determine the design axial load strength for the column, and we're actually also going to determine whether or not we have enough spiral reinforcement. So this will be a pretty good example. So here's our column. Okay. So we know it's 4 KSI concrete. Sorry. And 60 KSI steel. I guess I should be a little neater about that and say YT. So sub that a bit. Okay. Now, we have a 15-inch column, okay? The first thing I'm going to determine is what's D sub C. D sub C is the diameter of the core, and what we do in concrete design is we take that calculation pretty easily. We take the diameter and we just subtract off the cover. So if I have the diameter and I subtract one cover this way and one cover this way, what's that going to leave me with? 12 inches, there you go. So 15 minus 2 times 1.5 inches, which is 12 inches. The reason why we need the core diameter is because we're going to need not only the gross area of the column, but we're going to need the area of the core as well. So the gross area of the column is going to be pi d squared over 4, or if you want to use pi r squared, you're more than welcome to. You can divide by 2 and then use pi r squared, or just do this. I think it's a little easier. So pi over 4 times 15 inches squared. And then we're going to need the area of the core. That's going to be pi dc squared over 4. So pi over 4 times 12 inches squared. That should be pretty easy.
The gross area, 176.7.
And somebody else, what's the area of the core? So 113.1. Sound good? Now there's two other things we're going to need. We're going to need the area of the transverse or the reinforcement along the column. And so that's AST. That's just 5.5 square inches. But we're also going to need one other thing, and that's the area of one of the bars for spiral reinforcement. So what is the area of a spiral bar? Anybody know? Say it again. No. Okay. So hold on. No, we're going to digest that one a little bit. First off, it's a number 8. The area of a number 8 is not 1. The diameter of a number 8 is 1. Okay? Make sure that you're aware of that. But we're not talking about the bars going in and out. We're talking about the spirally reinforced bars. What is the area of a number 3? 0.11. There you go. And if you don't remember, you can always just say pi over 4 times what squared? 3/8. Because it's a number 3. Anything below, remember, that's the diameter, not the area. Okay? So this is 0.11 square inches. So I don't think there's anything else that we need. I mean, we have everything else here. We know the diameter of the bars and whatnot, and so on and so forth. So we're good there. Okay. So the design capacity is really easy. Monitor's not liking me. So, first off, what's our formula? Well, it's phi times alpha times a big quantity. And that quantity is 0.85 FC prime times the area of the concrete plus Fy times the area of the steel. That's easy, okay? And so we can plug and chug, except we're missing a couple values. What are we missing? Phi and alpha. What are phi and alpha going to be for this column? 0.75 and 0.85. They're always going to be higher than for tied columns because spirally reinforced columns serve to confine the core of that column a bit better. So they're going to, so that's going to result in improved behavior under those conditions where it's close to failure. So we'll say phi 0.75, alpha is 0.85. And the answer why, because it's spirally reinforced. So that's 0.75, 0.85, what was AST again? Oh, there, I put it up there, yeah. What do we got? wait, did I mess something
Should
up?
that be
Yeah.
AST?
This is wrong. That's wrong. That's that, right?
Yeah.
All right, yeah.
I got 701.1.
701.1.
581.
There's 2.85s. That might be it. Because this, remember, this is a big quantity, and there's two of these. Maybe do this, and then these two on the side. Because that's what I got, 581.5. Kips, right? Sound good? Did you get yours? No, take time. This is important.
I'm so sorry.
No. You're doing the counts. I want to take the time to make sure it's right. You might be getting it right. They might be getting it wrong. I'm going to be getting it wrong. You got it? Okay. It's easy to throw parentheses in the wrong spot here, which is why, look, again, I know exams can seem like time crunches. I always recommend that you do a calculation once, then immediately do it again. Just see if you get the right answer. I mean, I don't know about doing 2 times 12. I mean, I think I could probably do that in my head. But something like this, do it, and then just do it again. And so, just like completely fresh. So, it will reduce errors overall. Okay. Next, we're going to do the spiral steel check. All right, and what I'm going to do for that spiral steel check is this. I'm going to use a little bit of a different notation than what's in the slide, but I'm doing that to just make sure you're crystal clear as to what we're calculating and why we're calculating it. So the first thing I'm going to calculate is the actual row S. And what I mean by the actual row S is this is how much steel is actually in the column, okay? So when I compute for AS DC minus DS over S DC squared, I want it to be clear that that's a measure of how much steel is in the column, okay? Now there's one dimension we haven't looked at, but that's pretty easy. So, and that's this DS. Oh, I'm sorry, hold on. That's a capital D. That's a capital D. Okay, so up top we have 4 times, what's AS? 0.11. DC is, now minus DS, anybody have a guess as to what DS is? First off, it's got to be a length measurement, because I'm thinking inches minus something's got to be inches, so.
1.5.
Well, no, it's not the cover. We already took into account cover when we did this. It's the diameter of what bar? The spiral. It's just the diameter of a spiral. And if it's a number 3, what's the diameter? 3/8. There we go. And then on the bottom, we have S. Now, S is how far apart those spirals are pitched. And what is that? 2 inches. And DC, that's 12 inches squared. And so what do we get for this? Well, that's a good question. You tell me. What are we calculating? We're calculating a reinforcement ratio. Remember, row values have always been small, so it's okay if it's a tiny number.
01776.
So we'll say that. What are we thinking? Sound good? Now, that's our actual row S value. Now let's calculate our minimum. And our minimum comes from ACI. So remind me what those two areas were again. I can't remember.
176.7.
What about the bottom one?
113.1.
4 KSI and 60 KSI. So what does that come out to be?
Oh, the area.
That's the area of the core, yeah.
I got 0.0168.
0168. You know what? I'm going with her on this one. Deal with it. We all know that we could break out the Excel and you know, and hash it out. There was a funny chart on it was a pretty funny meme, and it was, you know, like time was on this axis, and on this axis was like math difficulty. And what it is, it started out here, it was like, okay, arithmetic, algebra, and then maybe like your trig, and then you graduate high school, then you get into college, and it's like calculus, differential equations, then you get into your career, and it's spreadsheets.
Well, Austin just seconded me on that 169.
Second to Janie on 168.
Don't make it clear and second.
She was first. So, all right, all right. Let's go back to behavior, though. What is this? Tell me. Interpret this. What do we have here? What does this mean? We have the actual reinforcement ratio. We have the minimum reinforcement ratio. So we're good. There we go. We have more steel than we need. So that's what this is saying. So we're good. Now, this should also, you know, if we're starting to have this discussion where, you know, provided values are greater than or equal to our minimums, if we're starting to get into that discussion, then ultimately what we're getting into is a discussion about design. What I've been doing up until now is I've been saying, here's a column, here's the reinforcement, the material properties, all that crap, and then what's the capacity? That's good, great, grand, and wonderful. But this is reinforced concrete design. So let's flip it around a bit, okay? You have a frame, you know? You have a building. Here's the ground. And we're looking at this column, and we know it has a dead load of 250 kips and a live load of 300 kips. By now, you should be able to determine those from CE 312, right? Structural analysis, build a RESA model, put your loads on there, determine your results. By now, you should be able to do that. Well, that's great. If I know that the dead load is 250 kips and the live load is 300 kips, well, how big of a column do I need to provide in order to safely resist those loads? Well, that's what reinforced concrete design is all about. Fortunately, I'd argue of all the designs that we do, in not just in this course, but in design overall, design of a reinforced concrete column, neglecting the effects of buckling, is by and large the easiest thing you'll ever do. Column design is pretty straightforward. So all you do is this. You determine your load on the column, your factored load, axial load, whatever. Then what you need to do is guess a reinforcement ratio, okay? Typically, well, first off, your reinforcement ratio has to be between 0.01 and 0.08. Like that's just, you have to do that because ACI requires that. A good starting value is 0.02, okay? Typically, we want columns to use a little bit of a smaller amount of reinforcement. So I'm estimating a value that's a little on the lower end, but not too low that I'm not going to have to go back and iterate this thing like crazy. Once we do that, what we do is we solve for a required gross area, then we use that gross area to determine the amount of reinforcement. Now these two steps here, if there's anything that's a little confusing, it's these two steps, okay? So let me sort of illustrate that. Now, first off, we're going to guess a reinforcement ratio. Why are we guessing a reinforcement ratio? Well, let me go back a slide. Let's just make sure that everybody's clear on what we're doing. Here's the capacity formula. So we have VPN is phi times alpha times this big quantity, 0.85 FC prime. We have AG minus AST plus FY AST. That's our capacity formula, right? Now, why are we guessing a reinforcement ratio? Let's say, for the sake of discussion, that we use a reinforcement ratio of 0.02, just like, what's suggested. Why is that important? Well, the reason why that's important is because right here, instead of AST, what I can do is I can rewrite that. What can I rewrite that as? I can rewrite it as 0.02 AG. And I can rewrite this as 0.02 AG. How can I do that? Well, what is rho? It's AST over AG, right? Just multiply over. Well, why does that matter? Well, let's do a little bit of algebra. What do all these terms inside here have in common? Inside the brackets. AG. So what I can do is I can say, all right, let's pull AG out of all this and divide. So here's my slide, and I'm looking at these red terms right here. That's the area of steel. I'm going to replace that with rho times the area of the column. Pull the area of the column out because I can factor that out. So inside this parenthesis, so pay attention here, AG minus rho AG, pull that out and I get 1 minus rho G. Does everybody see that? Here, I just pull it out and I get this. Well, VPN has to be greater than or equal to PU, divide, and I get this. Keep in mind, this is design mode. That is probably one of the most fundamental expressions that we need in order to determine the area of that column. Because if we know the area of the column, think about it like this. Let's look over here. Let's say I compute this. Let's make up a number. Let's say that's the minimum gross area. If it's a square column, tell me what to do. What do I do with that number if the column is square? You're in design mode. I want you to tell me how big that column needs to be. Say it again. Why am I taking the square root?
Figure out the size of the column.
There we go. So if I have a square column, the gross area is d squared. So therefore, actually, let me not use d. Let's not use d. Let's use b. Because that's what we've been using for width dimensions. So b minimum is the square root. And so what is that? Just have some fun with it. 12.11 inches squared. No, inches. Is everybody okay with that? So here's the thing, and what's going to be kind of wild here in a second. Well, actually, let me not get ahead of myself. Let's not get ahead of myself. Let's say it's a circular column. What do I do? Here's my minimum gross area. What do I do? So the gross area. Take the circle root. That was true. What do I do? What do I do in order to determine the minimum diameter? Say it. Somebody. You said. What did you say?
Square root of 4 AG over 5.
There we go. So flip and multiply. So what do we do? We say AG and then is that what we call it?
Yeah.
The circle root. Did you like that? You just take that to the bank. What do we get here? I'm just curious. 13.67. Okay. Now, this is important. I'm actually kind of happy that the values worked out like this because I did it again. I'm all about making this dimension squared. It's that circle root. It sort of threw me for a loop. It's your fault. Okay. Okay. Ooh, all right. We're gonna have to call it after this, but I do want to make a point. I want to make a point on something. This is the last point I want to make today. I want everybody to pay attention to this. Okay. We typically specify column dimensions in even numbers, like 12 inches, 14 inches, 16 inches, 18, something like that. Keep it simple, typically. So if I got these numbers, probably what I would do is I would say use D is 14 inches. What I would probably do over here is use B is 12 inches. You're like, wait a minute. You wrap it down. You can't do that. Yes, I can. I'll explain why next time. But if you want a spoiler alert, the reason why is because to determine the required amount of steel, I'm not going to take rho times this. I'm going to take my actual column area and then solve for how much steel I need. And so we'll go into that next time. So, that's all I got. Yeah.
Once we figure out how much steel we need, is that how we determine the slope of the spiral? Like if we have like a 20 column, like how do we
No. There's another process to that. It's not hard, but there's a little more to that. We're going to do that in 19B.